Okay, so let's go ahead and solve an example. In this example, a circuit has been given to us. The circuit has three different sections. There's a section called source, there's a section called line, and there's a section called load. So these sections are really provided to you to give you an idea about like what's going on. It doesn't really change our circuit analysis. Like it's still a circuit with a voltage source and bunch of impedances. Like you have a 1 ohm resistor and you have a J 4 ohm inductor. Remember from chapter 9, an inductor in a sinusoidal steady state becomes a like an imaginary resistor, right? And then you also have another resistor here and another inductor here. So at the end of the day, you have a bunch of real and imaginary ohms to deal with, right? But then it's trying to tell you that imagine that like basically it's trying to give you a picture that you have a source, like imagine that you have a power plant here, you have a line, meaning that, well, you have some transmission line, and then you have a load, right? This is like, let's say this load is representing the power consumption at a household, right? Or a factory, or whatever you want to think about, right? That's why you're seeing that the load has higher numbers in terms of resistance and inductance compared to the line, because line is supposed to be ideal, but well, in this case, because it's a long transmission line, it's not perfectly ideal. It has a little bit of resistance and a little bit of inductance. But that's just context. From the circuit analysis point of view, so this is just for you to understand what does load, line, and source means. From a circuit analysis point of view, this is just a simple circuit, voltage source with a bunch of inductors. So let's actually start analyzing it. So part A asks us to calculate the load current IL and voltage VL. So basically this voltage, again, it doesn't matter if it's called load current or apple current or orange current. The important thing is that it wants us to find IL and VL. IL is defined as this, VL is defined as that. Let's do that. So how do you go about the circuit like this? Well, KVL, that's the simplest thing. I know that if I write KVL 200 plus 250 with an angle of 0 minus 1I minus J4I minus 39I minus J26I is going to be 0, right? So basically, I can say that it's all of these are in series, so IL is really the current that is going through all of them. So IL is going to be 250 with an angle of 0 divided by, well, the addition of all these complex numbers, which will give you a 40 plus J30. Okay, so if you convert this to the polar format, the denominator to polar format, and do the math, you're going to get 5 with an angle of negative 36.87. Okay, now that's the current. What's the unit for this current? Of course, it's amperes, but there's one other thing that we have to mention here. The voltage that has been given to us is actually an RMS voltage, right? So you can imagine that, well, I can still work with an RMS voltage, but the current that I'm going to get is going to be also RMS. So I'm going to write amperes, and then in parentheses, I'm going to add RMS here. Okay? So that's all you needed to know. Now, how do I find VL? Well, similar to any other circuit, I have an impedance here, and I know the current through this impedance. So the impedance times the current is going to be the voltage, right? Similar to Ohm's law. So VL is going to be ZL times IL. So it's going to be 39 plus J26 times 5 with an angle of negative 36.87 degrees. If you do the math, you're going to get 234.36 with an angle of negative 3.18 degrees, and this is also volt RMS. Okay, so that's part A. So all I did was KVL, and I just used Ohm's law with, well, complex number, kind of an Ohm's law, but Ohm's law at the end of the day. Part B is asking us to calculate the average and reactive power delivered to the load. So basically, it wants us average. If it's asking for both real or average and reactive, it's kind of asking us for the complex power, right? So it wants us to calculate the complex power of the load, this part, this impedance, the 39 ohm and the J26 ohm. How do I find that? Well, again, I'm going to use the equations that I know. So this was part A. For part B, I know that S is going to be, since these are effective values, I don't have the 1/2. I'm just going to write, it's going to be VL times IL complex conjugate. And that's as simple, it is as simple as that. So VL is 234 minus J13. So I converted this polar format number, 234.36 with an angle of negative 3.18, to rectangular format, and it became 234 minus J13 times the current, which is, again, if I convert this from polar format to the rectangular format, I'm going to get 4 plus J3. You might ask, why did you do that? Well, you could, because when you're multiplying, the polar format is actually better. Yes, you could have done that. I just wanted to show the complex number with the real and imaginary part of VL and IL. But indeed, you have to actually multiply them with the polar format, and then if you want, you can convert it to rectangular format. So if you do that, at the end of the day, whatever you do, you should get S equal to 9. Oh, one other thing. So this 5 with an angle of negative 36, you can imagine that the imaginary part, so I'm talking about this number, the imaginary part is actually negative, right? And notice that the imaginary part of this number here is actually positive. So if you convert this to the rectangular format, it actually is equal to 4 minus J3. So it's minus J3. But because I have this complex conjugate, it becomes 4 plus J3. So that's something I wanted to make sure that you guys know. So now, if you do the math, you're going to get 975 plus J650. And you have to have it in the rectangular format. Even if you do the math in polar, you have to, at the end, convert it to rectangular. Why? Because we know that S is equal to P plus JQ. And the question is asking us to find average and reactive power delivered to the load. So I need the real and imaginary part. So this is going to be P, and this is going to be Q. So I'm going to have 975 watts delivered to the load plus 650 volt amp reactive delivered to the load. Okay. Now part C is asking us to calculate the average and reactive power delivered to the line. So meaning that, well, since this section is called line, it means the same thing for this impedance. There's a difference here that for the part B, I had VL and I had IL, right? So I could actually go ahead and calculate S, right? But now for this one, I don't have VL yet. So one way to do this is basically using the same thing that I did in part B, meaning that just calculate the, let's call this, so method number 1 would be calculating this voltage, let's call it Vx, and then S is going to be equal to Vx times IL complex conjugate, right? So that's number 1. So you can actually do this, and if you do it, you should get something like basically equal to 25 plus 100, J100. So P is equal to 25 and Q is equal to 100 watts and volt amp reactive. The other way to do this is that if it was only resistors, we knew that, well, since I have the resistance and I have the current, I really don't need to actually calculate the voltage to have the power, because we knew that for resistors, P was equal to VI, and it was also equal to RI squared, because V was RI, and it was also equal to V squared over R, right? Now I wonder, here I don't have a resistor, but I've noticed that everything that applied to resistors kind of more or less applies to impedances. So I have a Z. So can I say it's basically ZI squared and V squared over Z? Well, we have to actually dig deeper into this. So this is really not part of the solution of this example, it's part of the lecture here, right? So if I actually look into this, I can see that, well, S is equal to Z, it's equal to V times I complex conjugate, right? That I know for sure. So it's V times I complex conjugate. And I know that V is equal to Z times I times I. So S becomes Z times I complex conjugate. So what would be the I times I complex conjugate? Well, if you think about a numerical example, or like basically the polar format of a complex number, we said that if x is 2 plus 3j, x complex conjugate is equal to 2 minus 3j. In the polar format, I can say if x is equal to, I don't know, 5 with an angle of 21 degrees, x complex conjugate is equal to 5 with an angle of negative 21 degrees. Okay, so knowing these two, when I multiply x and x complex conjugate, what I'm going to get is, well, 5 times 5. So magnitudes are going to multiply 25, but the angle is going to be added together. And since the angles are opposite of each other, I'm going to get an angle of 0. A complex number with an angle of 0, it means that it doesn't have any imaginary part, it's all real. So this is really 25. Therefore, I can say that when I have x times x conjugate, the multiplication results in the magnitude of x squared. Okay, so this is not really part of circuit, teaching circuits. It's really complex math, which I hope that all of you know, but this would be a really quick reminder, right? So based on the above, I can say that zi times I conjugate is going to be z times magnitude of I squared. Okay, and then knowing that z is equal to r plus j x, I can simplify this to r magnitude of I squared plus j magnitude of I, plus j times x times magnitude of I squared. And now I can see that my s is divided into two parts. One of them is real, so I can say this is P, and the other one is imaginary, so I can call this Q. So really my P, the real power, is the real part of my impedance, R, times I squared, and there's no surprises there, right? I can imagine that if I have a resistance that is the real part and I have a current that has, well, it's a complex current, but if I want to calculate the power, it's going to be Ri squared. For any resistor, at the end of the day, the real power should be Ri squared. And then there's the imaginary part, which is Xi squared as well. So now going back to the example for part C, method 1 was this. Method 2 would be P is equal to, let me use a different color. P is equal to Ri squared. So R is 1 times 5 is the magnitude of I is basically this 5 here. I don't care about its angle. So it's going to be 5 squared. So it's going to be 25. And Q is equal to X I squared. So X being 4 times the magnitude of I, which is 5 squared, is, well, 4 times 25, you get 100. This is in watts, this is in var. Okay. Now part D is asking us to calculate the active and average and reactive power supplied by the source. Okay, so again, we could solve this in two different ways. So number one, well, the power that is supplied by the source is either consumed by the line or by the load. It cannot go anywhere else because, well, energy is preserved. So I have the power consumed by the line and I have the power consumed by the load. I just need to add them up. So S of the source is equal to S of the line plus S of the load. Of course, the power, this is the power delivered by the source, and these two are the power consumed by the line and load, right? So basically, they should be equal in magnitude, but well, the sign is different. If you want to actually express the power consumed, then the power consumed by the source would be negative, but then since I'm talking about the power provided by the source, intuitively, well, if you provide something by the source, you should consume an equal amount of power by the line and load. Okay, so this means that I'm going to get for line I have 25 plus 100J or J100, doesn't matter, plus from the load I have 975 plus J650. So it's going to be equal to 1000 plus J750. And the unit is volt amp because it's S. Now, is there any other way to actually calculate this? Yes. The other way is that, well, it's a source and I have the voltage across it and I have the current through it. So like any other component, I know that S is equal to VI complex conjugate. So all I need to do is to multiply 250 by the complex conjugate of the current that is being that is passing through. But then since I'm so if I calculate this, it's going to be equal to, again, I'm going to have 250 multiplied by, and the current is, well, 5 with an angle of that, or I can just say the complex conjugate of I is 4 plus J3. And you can see that 250 times 4 is 1000, and J3 times 250 is J750. Okay, so either way, you should get to the same answer. Remember that the power that is, this is the power delivered by the source. If the power consumption of the source was, so let me actually write it. So this is delivered by the source. So this means that power consumption of the source, then that would be negative VI complex conjugate, then it would have been, well, negative 1000 minus J750. So this is just to avoid any kind of confusion, because from chapter 1 you remember that we checked the power balance. We made sure that the addition of all the power consumptions is equal to 0 in a circuit, and since we have the consumption at the load and the line, the consumption of the source becomes negative if you actually remember those V and I directions, basically for this case, because the current is actually coming out of the positive terminal, the power consumption is going to be equal to, for the source, it's going to be negative VI's conjugate, and that's why you get a negative number. And then if you add this with the power consumed by the line and the load, you will get the 0, so therefore you get the power balance.